So an implicit function is a function that is described in terms of y and x versus an explicit function which is described with just x. Okay, usually an explicit function. So an example here, over here, our explicit function is y equals square root of x square root of 25 minus x squared. And we can write it as a function g of x equals square root of 25 minus x squared. So this is essentially what we normally see in explicit function, y equals form. So implicit function is slightly different. So this is actually a semicircle function, and we can actually express the semicircle function in terms of x squared plus y squared equals 25, or in this case, it's the radius squared, which is 25. So this is an implicit function. It's the same function. This happens to be the whole circle instead of just half the circle that we have over here in this y and g of x form. But notice that it's not a y equals format. The x and y are both used to describe that function. Okay. So this is an implicit function, and our Desmos calculator, our Desmos graphing tool will graph these nicely. We can also graph them, in this explicit form. But we're going to start moving towards a more of an implicit form of expressing relationships. And so we want to know how can we differentiate those. So we're going to do something called implicit differentiation. So implicit differentiation is based on applying the chain rule. Okay, so we essentially are just going to apply the chain rule to a function. And so when we need to understand, when are we going to apply this chain rule? Well, we apply chain rule when we have an embedded function. So a function inside a function. So if we take a look at the notation here, we have f of g of x. Well, if I were to differentiate this, I'd differentiate the outside function. So I'll just kind of write it out here. I differentiate the outside function f prime, and then we would differentiate the inside function g. Okay, so then there's my g embedded, and then we apply the chain rule and differentiate g prime like that. Okay, so when we take a look at this expression doesn't have to be, f of x equals something. This expression could be embedded inside any expression. So an example here we have in our x squared plus y squared equals 25. This is actually an embedded function. So notice that the outside function is squared and the inside function is y. So y is embedded inside the squared function. The x is just normal. We differentiate with respect to x, but this y happens to represent a function of x. Okay, so we cannot differentiate explicitly in terms of one variable, so we need to apply implicit differentiation. So as we hit these embedded function, we need to apply the chain rule. So the way it works is this then. Okay, so we're going to just kind of practice using this idea in this strategy. And as we use this, we'll talk about more and more of kind of how to get at the depth of the meaning. Okay, and it is a little bit hard to wrap our heads around at first, but it's actually quite easy to do if you understand what you're looking for. So I'm going to demonstrate how we do this. So we're going to differentiate this x squared plus y squared equals 25. So when I differentiate this expression, I'm going to first of all differentiate all the x parts of this expression just normally. I'm going to differentiate that as 2x. Okay, so it looks like this. I'm going to get 2. I'm just going to change colors here. Okay, I'm going to get 2x. Okay, there's the derivative of x squared plus. So then I'm going to differentiate the y squared. Well, I'm going to differentiate the y normally. Okay, so I was just going to differentiate this as, power rule. So I end up with 2y, no problem. But now, since y is an embedded function, anytime I differentiate y, I need to make sure that I apply chain rule. So I'm going to times by y prime. Then we get equal to, and then the derivative of 25 works out to be 0. So there I've generated my dy by dx. So there's my dy by dx, which is same as y prime. And I've generated a derivative, which is the change in y over change in x. It's right there. There's my change in y over change in x. Okay? And I just want to make sure that I can find that. Well, I just need to isolate that algebraically. So when I rearrange this, I get 2y times y prime equals negative x 2x, and then solving for y prime is equal to negative 2x over 2y. I'm going to simplify that to negative x over y. So there is my derivative. If I want to find the slope, I can use this expression, negative x divided by y. So if I want to find the slope at some particular point, I just plug in the x coordinate in the numerator, the y coordinate in the denominator, and that will give me my slope, or the change in y over the change in x.